Hello, my name is Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And this talk is entitled The High Bar for Interpretable Machine Learning in Housing, Homelessness, and Health. And this is a talk I'm going to be giving at the Transdisciplinary Scholarship Day, or one of the Transdisciplinary Scholarship Days being held at the University of Calgary in June 2023. And I want to start out by just saying how grateful I am to have been able to live, work, and raise my family on the territories of the Treaty 7 people. This includes the Blackfoot Confederacy, so the Siksika, the Piikani, the Kainai First Nations, as well as the Tsuut'ina First Nation, the Stoney Nakoda people, including the Chiniki, Bears Paw, and Good Stoney First Nations. As well, the city of Calgary is located on the territories of the Métis Nation of Alberta, Region 3. So, if I'm going to be talking about housing, homelessness, and health, I want to start off by giving a little bit of context. So, um, if we look at Canada-wide, in 2016, 235,000 Canadians experienced homelessness. If we look a little bit more locally at Calgary, in 2018, the point-in-time count, which is just a one-day count of people experiencing homelessness in Calgary, found 2,911 people. And if we even dig a little bit deeper, or look more closely at the people in Calgary experiencing homelessness, we've learned that 47% of these people are accessing emergency shelter services. 44% have been diagnosed with a physical or mental disability. 51% have been diagnosed with an addiction, and 47% have been physically attacked in the last year. And these numbers are from a study done for the Calgary Recovery Services Task Force. And the purpose of these numbers is to just give you an appreciation for the whole host of challenges facing people experiencing homelessness, but also to reinforce the idea that it's really hard to separate housing, homelessness, and health. Everything has to be considered together when trying to develop tools to help these people. So in our work using data in the housing and homelessness and health sectors, we basically have three kind of guiding principles for the research that I'm doing. The first one, kind of as shown in the previous slide, is that housing and homelessness, or health and homelessness, are essentially inseparable. So, someone who is experiencing homelessness almost certainly has some pretty complicated and serious health challenges as well. And that means when we're working at putting somebody into a house or a home, we have to focus on their healing at exactly the same time. So it's not enough just to put somebody in an apartment. There have to be supports around that person to help them deal with any mental or physical health challenges that they have. And finally, the third tenet of our work is the notion that any kind of healing has to occur in relationship between two humans. And this is particularly true for mental health. And so when people think of using data for housing and homelessness, one of the concerns sometimes that surfaces is that we're developing tools to replace the humans. So the machines are going to replace the humans, and the machines are going to decide who gets connected to supports. And that is absolutely against everything that we're working on in my group. So this concept of healing in relationship necessitates a human interface to any housing or health system of care. So there has to be humans helping humans is fundamental to any successful system of care. But data still has a role to play. So data can still help with better decision making. And in a frontline setting, whether it's in housing, homelessness, or health, the cognitive load of accessing data can sometimes be really high if the data systems are clunky, or data requires a lot of searching, or you have to read a lot of text in order to kind of summarize information. And basically our research goal is to make it easier for frontline workers to access and use data in their care decisions when making a care decision. So the question is, how should machine learning then be used to support frontline decision makers? And the analogy I like to make is the blood pressure cuff analogy for housing and shelter. So when you look at a caseworker in a housing support program, or an emergency shelter, they make decisions a lot like a physician makes decisions. So they'll talk to a person about their history. You talk to your patient or your client about their history, what have they been experiencing. You take their current condition into account. But physicians also have access to a whole bunch of other ranges of tools, medical measurements. So things like blood pressure, lab tests that give them specific or give them information about risk factors for specific medical conditions. So, for example, when my doctor puts a blood pressure cuff on me, if my blood pressure is high, that indicates that I'm at risk of um, a series of cardiovascular related complications. Now, the blood pressure cuff by itself doesn't make a care decision. The physician still takes into account everything else that's going on with me before, perhaps prescribing blood pressure medication. But it's a useful input to that decision-making process. And what we want to do is develop data-based tools that are useful inputs to the housing and homelessness care decision-making process. So in other words, could we use machine learning to make a housing intervention blood pressure cuff? Or maybe said more accurately, could we use machine learning to estimate whether or not a client is at risk of a particular type of adverse outcome? Again, not to replace the human decision maker, but to give that human decision maker a little bit more information for making a care decision. Now, machine learning, in order to be adopted, also has to be interpretable, and there's a very high bar for this interpretability. So workers in both homelessness systems and health systems are making very, very high stakes decisions, whether or not to connect somebody to a home, or whether or not to provide a certain type of health intervention. It can be life and death. And the people making these decisions know that. And so they're not going to trust a data tool that they don't understand as part of this decision-making process, because ultimately the responsibility for the consequences of the decision rests with them. And this means that the tools must be interpretable. Now, the good news is that interpretable machine learning is a whole area of research, which is the area that we're involved in. This is also sometimes known as explainable AI, XAI. But a lot of, particularly explainable AI helps very technical people understand things like, deep learning models, how they work and respond to certain inputs. They're not necessarily going to be interpretable for a non-technical person. And this is the bar that we're trying to achieve. So interpretable for our context means that a non-technical frontline staff person should be able to fully understand how our tool estimates risk, and be able to validate the operation of the tool based on their own experiences. And I'm going to give you two examples. One is the rule set search algorithm, and the next is a nearest neighbor sequence estimator that I believe meets this high bar of interpretability. Okay, so in the spirit of interpretability, rule set searches can be explained fairly easily. So if you're going to use a rule search algorithm, the first thing you identify is an outcome that you're interested in, so something that can happen to a person. And then you dive into data that describes that person and identify events that are recorded in the data that you can add up over a certain time interval. So you can add up the number of times somebody accesses shelter, for example, or the number of times somebody checks into an emergency room. And then using historical data, what you do is you find the best combination of threshold style rules that predict whether or not that outcome is going to occur. So you've got a historical data set filled with a whole bunch of different people. Some of them experience the outcome, some of them don't. You add up the events that occur for those people over a certain time interval, and you come up with thresholds to try and predict whether or not the event happens. And once you find the best set of threshold rules, you apply these rules to the event totals of new people to see whether or not they're at risk of experiencing the outcome. And so to explain this with an example, um, from 2007 to 2020, the Calgary Drop-In Center saw on average 268 new clients per month. However, the interesting thing about these clients is that most of them don't stick around for a very long time. 85% of them are transitional users that are here for a very short amount of time, in shelter in a very short amount of time. A small minority, only 3%, turn into very long-term or what are sometimes known as chronic shelter users. And it's these long-term so-called chronic users that tend to be prioritized for supportive housing. However, how do we know who is a long-time shelter user? Well, the first approach is to wait a long time, but this is a terrible idea because you're forcing somebody to stay in shelter a long time, and it's not a very good place to stay either for your physical or mental health. So that doesn't work. A better approach is to see if we can find a rule set that we can apply to patterns of early shelter use that identify whether or not somebody is at risk of becoming a long-term shelter user. And if they are, we refer them back to our human for follow-up and more discussion. So again, these rules don't exist to replace the human decision maker. It's just another way of connecting people in shelter to support workers. And so the Calgary Drop-In Center has a data set that we've been able to work with that records data on every interaction that their clients have with shelter services, so sleeps, counseling sessions, security incidents. We did a rule search algorithm, and we found that people who are likely to become long-term shelter users, if we look at their first 60 days of shelter access, these are people that sleep in shelter a lot, 54 times or more, and interact with counselors 11 times or less. So these are people that are in shelter a lot, but they're not really very actively engaging with support services. And this rule has a precision of 71%, which means 71% of the clients identified by the test actually do become chronic. And the recall is 77%, which means that this rule set identifies 77% of all the people in the historical shelter population that become chronic. Now, again, remember, these rules are meant to be used in a system where there are human caseworkers that are interacting with clients using a bunch of different mechanisms. This isn't the only mechanism for referring people to care. And so if our test misses somebody, chances are they're going to get, they're still going to be interacting with support services through some other mechanism. And if we refer somebody to a caseworker who isn't actually going to ultimately become a chronic shelter user, that's okay because that's what the conversation is for. The caseworker can ascertain that once they're referred to connect with the person. The second example is something known as nearest neighbor sequence estimation. And so basically the way this algorithm works is you identify a person that you're working with, maybe you're a caseworker and you're interacting with a person, and determine how, and take a look at their data and determine how this person has interacted with different system supports over a period of time. And then from historical data, find a cohort of people that have access to who have access services in a similar way to the person that you're working with. Their access pattern is similar to the person, and I'll be more specific about what I mean by similar in a second. And then once you've identified your cohort of similar people, you basically take a look at what that cohort experiences next in their historical records to get an idea of what the person you're working with might experience next in their actual sort of real-time interaction with the support system. And so this example works with data from the Calgary Homeless Foundation, which aggregates data from over 144 different housing and homelessness programs in Calgary. And for when we select a particular person in this CHF data, let's say this is our person of interest that maybe a caseworker might be working with, we create our cohort of people who are similar to that person by basically sort of going through two steps. The first step is we look, if we're looking at a particular time point for our person, we find everybody else in historical data who is accessing the same service at the same point of time in their data record, right? So if our person is in shelter after 30 days, we look for everybody else who was in shelter after 30 days, plus or minus a certain window. And then we retain only those people from that cohort who have had historical data records or system patterns that are similar to our person of interest. So for this particular example, I define that as people who have days that are 75% the same as our person over the last 2 years. And once we identify our cohort, we then sort of look 30 days into the future for our historical cohort and look at the mix of outcomes they experience to get an idea of what our person might experience. And here's a graphic that shows what that looks like. So at the top part, we have, let me see if I can. So in this top part of the graph, this is the timeline for our person of interest. So this represents one individual's the way they access services in the housing and homelessness sector. So we have a series of sporadic shelter accesses that start in 2009 and continue through to 2010. Then we have a gap, and then the person accesses housing services for a period of time, and then another fairly sizable gap, almost a year. And then we see some, periodic shelter access, another interaction with homelessness services, and then some interactions with some other support programs. Now, the two figures, the figure in the middle and the figure on the bottom, shows the result of our nearest neighbor algorithm. So this middle plot shows the size of our cohort, so the number of people we found in historical data that look the same as our person of interest. And when the person was accessing shelter sporadically, there's a large number of people that also access shelter sporadically. So we were able to find over 20,000 people in the data that resemble our person of interest. And if we look at the outcomes for those people, about 90% of them would go on to experience a gap in their shelter use. About 10% would go on to continue to use shelter, and almost nobody in this cohort ended up in a supportive housing program. Now we can see over time that the number of people in our similarity cohort drops, and then for the period of time where we access housing, the cohort drops. It looks like to zero, but it's not zero, it's about 100 people. So that means that once we start accessing housing, we now have a shelter access pattern that's very unusual. So not very many people have sporadic shelter access patterns followed by a year of just not using the system at all, and then all of a sudden show up in a housing program. And so that means that by itself, the fact that there's not very many people that are similar to our person is useful information, because we know that we're dealing with somebody who's, not the typical, if you like. And also, it dramatically changes our outcomes. So now, the portion of people in our similarity cohort that continue to stay in housing jumps up to over 90%. The number of people that use shelter drops down to almost 0%, And also the probability of being in a gap is very low. So basically it means that once you're in housing, you tend to stay in housing. And so that's what we can maybe expect for this person. And so not to go through all the rest of this in a huge amount of detail, but you can see as the record for this person sort of continues to increase, the similarity cohort jumps up and down. So once we're out of housing, we again have a bunch of people that sort of look like our person. And then when we're back in shelter, we drop down to, about 1,000 people that look like our person. And, we fluctuate up and down. And we can see our outcome proportions also vary quite a bit. So this, for the period of time where our person is interacting with shelter and housing and programs, we have sort of a variable, probability of continuing to use shelter or ending up in housing. So, again, this is just an example of a method that just lets us know, when we're working with a certain individual, are there a lot of people in the data that have had a similar experience to this person? By itself, that's useful information. And of those people who are similar, what do they tend to experience 30 days into the future? And that gives us an idea of what we can expect for the person that we're working with. So to sum up, frontline human relationships and decision making are the most important part of any system of care, and any development of data tools or machine learning algorithms have to recognize that and support that rather than replace it. Data analytics and machine learning can play a valuable role in supporting human decision makers, and I hope these examples show how we can use machine learning ideas to process data in a certain way that make it easier for people to use, but still let the human caseworkers make the ultimate care decisions. And interpretable machine learning techniques are great, but interpretability has to make sense to the user, not to the designer. So again, when you're sort of looking at explainable AI, interpretable AI, there's a lot of concepts that are very useful for somebody who's very familiar with data and data science. But once we, make interpretability mean that we have to be able to explain this algorithm successfully to non-technical people, then interpretability has an even higher bar.